Hello. Today my partner and I are going to introduce hyperbolic functions. And why is hyperbolic function so special? It's because sometimes we cannot describe a graph with natural polynomials. And so we have to use hyperbolic function to solve some math problems. And hyperbolic functions also have some characteristics of trigonometric functions. So let's look at the definition first. Here's the definition. We define hyperbolic sine as e power x minus e power negative x n over 2. And hyperbolic cosine is e of e power x plus e power negative x over 2, like this. And let's see the graphs. This is the graph of e power x over 2. And this is the graph of e power negative x over 2. And after we combine these two graphs together, we can get the graph of hyperbolic sine and hyperbolic cosine. By observing the two graphs, we can find some characteristic of the graph. First, you can see hyperbolic sine of x equals negative hyperbolic sine of x, of negative x, like this. And for hyperbolic cosine, is the opposite. We have hyperbolic cosine x equals hyperbolic cosine negative x. Okay. After introducing the definition of hyperbolic functions, let's calculate it. First, we want to know the derivative of hyperbolic functions. And here is how we do it. We'll take hyperbolics of sine, for example, and we can do other functions by the same way. First, we know that hyperbolic sine is like this. It's the definition. And after we have the definition, we can find the derivative by the knowledge we have already know. So just calculate, and you will get the e power x plus e power negative x over 2, and it equals hyperbolic cosine. And here we have to note this, that don't forget the chain rule, or you will get the negative sign between 2. Okay, and hyperbolic cosine, we can finish it in the same way. So find the derivative and don't forget chain rule. You will get the answer, and it equals hyperbolic sine. Okay, so this is how we find the derivative of hyperbolic functions. Then let's find the inverse function of hyperbolic functions of each. As the definition we have do in the past, it's the same. Taken same. Here's an example. If hyperbolic sine, the inverse function of hyperbolic sine x equals y, then it means hyperbolic sine y equals x. Here's the definition, as we do before. and the other functions, the definition are all the same. So I will not write it all. You can just do it by yourself. Then we want to know how to find the differentiation of the inverse hyperbolic function. Here's how we do it. First, we cannot just calculate it, so we have to do a transform. With that, y equals the inverse of hyperbolic sine x. So we got hyperbolic sine y equals x. And by the definition, we can write down this form. After we have the formula, we can change it into this form. Okay, then we have to make a transform again. Here, we multiply e power y to the formula, and we'll get the formula like this. And by the ways we all have learned before, we can find the root. Okay, and here we have to be careful that we know that the power of y should be bigger than 0. So here we have the answer is x plus the root of x squared plus 1. This is the answer. And we take natural log, and we'll solve that y equals natural log of the formula. It's the same. Just put it inside. Okay, so we have finished the transform. So we say the inverse of hyperbolic sine x is like this. We make it into the form of natural log. After we have finished the transformation, we can do the differentiate the inverse of hyperbolic sine, and it's not too hard. First, we have to open the formula. The derivative of natural log, we have put it. We can transform it like this. And don't forget the chain rule. You have to deal with each side that includes x. So it will look like this. This is the first area. Then this is the second area. And don't forget, this is an x squared inside. So we have to make 2x and multiply it. Okay, and after that, we can write the formula to a new form, and it will look like this. And we can find that we can eliminate the formula. So the answer is very easy. The derivative of the inverse of hyperbolic sine x is 1 over the root of x squared plus 1. And using the way, you can find the inverse function of hyperbolic cosine. By combining these two functions, you can do the rest. Okay, and next I've made a summary of the lesson. First, we have the definition of hyperbolic functions. It's for hyperbolic sine and hyperbolic cosine. And the rest are only the we can combine this to find the rest. Okay, then we talk about how to compute differentiation of hyperbolic functions. And this is at the beginning, I've said it has sounds that is kind of like trigonometric functions. And the only difference is the two is different, and the others are the same. And next, we have talked about how to find the inverse of hyperbolic functions. Then we have proved the hyperbolic sine, and you can try the same way to finish hyperbolic cosine.
Okay, so now we're going to show you guys some example. First, we will show you this example. We have to find the derivative of this function, and it's quite easy. Before we start, we can look up here. Here is a characteristic we mentioned before. Is that the derivative of hyperbolic cosine x is x squared minus 1 square root over 1. So by using this property, we can see that the derivative of y is second square minus 1 square root over 1. And don't forget that we have to use the chain rule. We have to have second times tangent at the back because of chain rule. Okay. And then we can simplify the function because we know that second square minus 1 equals to tangent square, and tangent square with square root equals tangent. So the function can be simplified to tangent over 1 times second and tangent. And by cancelling out tangent and tangent over 1, we can get second. So the derivative of this function equals to tangent. Okay, now the next question. It says that we have to show that the area of the shaded hyperbolic sector in figure 7, which is this one, is equal to half t. And here's a hint. It says that first show that the area equals to this function, and then verify that the derivative of this function is 1.5. Okay, so let's observe the figure. First, we can see that the shaded area is equals to the red triangle minus the blue stripe area. We can notice that. And then we will change the function, this function, into this function, which is quite obvious, so I won't do the calculation. And then we can see from the graph, the red triangle, the area of the red triangle equals to 1.5 hyperbolic sine t at times hyperbolic cosine t, which is quite obvious too. And the area of the blue shaded part, which is this part, we have to use integral for this one, which is 1 to hyperbolic cosine t, and which is here, and the function that we have calculated at the top. So we can see here to this one. Okay. Then the area we want to know is this part. The area for this part is the area for the red triangle minus the area for the blue shaded part, which is this. So we have proved this one, this function. Okay, now so we have to get the derivative for the function a. And let's look up here. Before we get the derivative, we can review some properties that we mentioned before. So the derivative for hyperbolic cosine x is hyperbolic sine x, and the derivative for hyperbolic sine x is hyperbolic cosine x. And also, the square of hyperbolic cosine h minus the square of hyperbolic sine h equals to 1. This is a very important property, and we can use it in many hyperbolic functions calculation. And also, we will use the fundamental theorem of calculus in this question. So let's take a look at it. It states that if capital F of x equals to this, then the derivative of capital F of x equals to the lowercase f of x. And this is the fundamental theorem of calculus. Okay, so now we have all the properties we need, so we can look at the derivative. So first, we can deal with this section. Have hyperbolic sine t and hyperbolic cosine t. For the derivative, we have to use the product rule. So first, we will derivative this section. Hyperbolic sine's derivative is hyperbolic cosine, and we times it with hyperbolic cosine itself. Then we have to plus hyperbolic sine times the derivative of hyperbolic cosine, which is hyperbolic sine. So by the product rule, we can get that the derivative for this section is this part. And this section, we can see that by the fundamental theorem of calculus, we will just simply plug in hyperbolic cosine h into the function. So we can get this. But we have to notice that because of chain rule, we have to times the derivative of hyperbolic cosine ht at the back, which is hyperbolic sine t. So this part is the derivative of this part. Okay, now we can focus on this the derivative of the a function. So by simplifying the function, we can get the function equals to 1/2 of hyperbolic cosine t squared and 1/2 of hyperbolic sine t squared minus hyperbolic sine t squared, because this equals to square root of hyperbolic sine t squared, which equals to hyperbolic sine t, and times hyperbolic sine t. So it will become hyperbolic sine t squared, which is quite easy if we know the property on top. So then we will simplify the function again. Then we will get that this function will become 1/2 of hyperbolic cosine t squared minus 1/2 of hyperbolic sine t squared, which we can apply the property we mentioned above, this one. We just times it with 1/2. So we can get that the answer is 1/2. Okay, so now we prove that the derivative of a function is 1/2. So we can also know that the a function is equal to 1/2 t plus a constant. Now, if we want to show that the a function equals to 1/2 t, we have to prove that when t equals to 0, let me change this. When t equals to 0, the value of the function is also 0, so that we can prove the constant equals to 0 and function a is 1/2 t. And this is obvious because from the graph we can see when x equals to 0, there's no area, it's just a dot. So of course, when the x is 0, the function's value is 0. Thus, we finish proving that the area of the shaded area, which is this part, will be 1.5 t. So this is the question and the solution. Okay, now we have finished the mathematical part of hyperbolic function. So now we're going to introduce something more interesting, is that the history of hyperbolic function and the application of hyperbolic function, since we didn't mention this part when we're in class. So we decided that we can do it in this video. So it all starts from a drawing of Da Vinci, which is this one. And we can focus on the necklace of the woman. We can see that, yes, the necklace. So Da Vinci wants to find a way to describe the curve formed by the necklace, which is like the statement below. If we fix the two ends of the necklace, so it hangs down naturally, like this, like the necklace in the picture. What curve is the curve formed by the necklace? We maybe will think that this curve is a parabola, but it's not. At first, Galileo Galilei thinks that catenary, which is the curve formed by the necklace, is a kind of parabola. He says this in his book, Two New Science. However, at 1646, Christian Huygens says that no, catenary is not a kind of parabola. He proved this by some mathematical way, but since it's a little bit complicated, we won't show it in this video. And until 1690, which is about 170 years after Da Vinci drew this picture, these three scientists finally determined what catenary is. And so this is the function that they conclude with. So catenary is basically a times hyperbolic cosine a over x. Or we can change hyperbolic cosine into the exponential way. So this is the function for catenary. Oh, and also catenary is called 悬链线 in Chinese. So basically, this is the history of hyperbolic functions. It's basically that the scientists want to describe catenary. So they create hyperbolic cosine and hyperbolic sine. Okay, so you may ask that why we mention catenary so much. It's because that catenary structures are very stable in the aspect of mechanics, and therefore it's widely used in engineering, which means that many structures in our daily life is in catenary. For example, suspension bridges basically all in catenaries because suspension bridge is fixed in 2 points, which is maybe here, maybe here and here. It's just like the necklace in the picture. It's fixed in 2 points, and naturally it will bend down because of the gravity. But also it's also affected by the tension of the rope. And this will just create a catenary, which looks like a parabola but not. And also we can see that this structure, which is the gateway arc, which lies in an memorial park in St. Louis. This is also a catenary. It also looks like a parabola, but it's not. Why it's a catenary? Because catenary is much stronger than parabola, so the structure won't be easily destroyed. So if we have time to visit America, maybe this is a place that you will want to go to. Okay, so now we will simply introduce some physics of catenary. This is the function of catenary, and A is a constant, which in physics we call it the catenary constant, and A will equal to this. And every sign in this function has a meaning in physics, so we will introduce it here. T0 equals to the horizontal tension of the point X, and G equals to the acceleration of gravity, and mu equals to the density of the rope, which correspond to what we just stated before. Okay, so this is the end of the introduction of hyperbolic functions, and we hope you will learn something from this video.